Gauteng. Right. As you go through your paper, you must be in a position to check the instructions and check what you're supposed to do. We know, as usual, that our questions are compulsory. You answer everything that is in the paper. And what is most important, I want to analyze question instruction number 9 and 10. Instruction number 9 says answer in full sentences, except when you have to state name, identify, or list. Which means when we have 2-mark questions, you must write a full sentence. You must write a full statement. When you are supposed to explain, explain fully. When you are supposed to describe, describe fully. When you are supposed to comment, you are supposed to comment fully in a full sentence. Then, the other important thing is on instruction number 10, the units of measurement must be indicated. When you are measuring, for example, it's a matter of determining the distance. You must indicate the unit of measurement. Is it in meters? Is it in centimeters? Is it in kilometers? You must indicate. If it's temperature, you must indicate how many degrees Celsius. If it's a matter of determining direction using bearing, how many degrees, you must indicate the units of measurement as you present your response. Is it in pressure? How many hectopascals? You must indicate in the right units of measurement. It's important because you'll end up losing marks for not indicating the units of measurement. Right, that besides our point. Instructions are important. They are part of the examinations and you must abide by the instructions of the examination. But we want to go and analyze our paper and try to figure out the right responses for the paper. Right. Let's go to our paper. Right. We go to question number 1. Question number 1, it says various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question number. Right. We are going to analyze our illustration, fig number 1.1, before we answer the question. I will try to explain what is happening with the illustration so that when we're answering the question, we'll just be figuring out the right responses from the questions. But we want to do an analysis of the illustration first. Right. We are seeing that we have this illustration. On this illustration, what do we have? We must note that on this illustration, what is important for us is to note the indications which are indicated on our illustration. Right. We have this anticyclone and we have this anticyclone. These are anticyclones. These are high pressure cells. Right. If we check on our map, this is the African continent, the Southern African subcontinent. And if we check our directions, this is the western direction. This is the eastern direction as usual. Right. So we are saying on the west, we are having an anticyclone, and on the east, we are having another subtropical anticyclone. This anticyclone on the west is our South Atlantic high pressure. On the west and on the east, we know it's our South Indian high pressure. These are our two anticyclones that affect the weather system on the interior of Southern African subcontinent. Right. So if you're having these two anticyclones, we are saying this is the South Atlantic high and this is the South Indian high. What happens with these anticyclones? We know that in the Southern Hemisphere, our circulation out of the subtropical anticyclones is anti-clockwise. Is anti-clockwise. Anti-clockwise meaning to say they reverse the movement of the clock. So the air moving out of the South Indian high pressure, it reverses the clock direction. It moves in this direction here. That is why we see that arrow B. The air is circulating out of the South Indian high. And also on the South Atlantic high, the air is going in that direction, reversing the clock movement. It's going against the clock direction. It's anti-clockwise out of the South Atlantic and South Indian. That is the circulation of air out of the subtropical anticyclones in the southern hemisphere. So because of this situation, we tend to find that the South Indian high pressure is featured by warm and moist air. The air which comes from the South Indian high pressure is warm and moist. And the air which is circulated out of the South Atlantic is cold and dry. Thus, the difference between the two air masses which come from the South Atlantic high pressure and the South Indian subtropical anticyclone. This one is warm and moist, so it's cold and dry. So we tend to find that the air which is driven out of the South Indian high is going to get to the interior from the east, and this is going to be driven to the interior from the western direction. Because of these differences in the two air masses, they have a tendency of differences in temperature and differences in their moisture content. They will meet somewhere in the interior, like as indicated here. These two air masses are going to meet. This one is cold and dry. This one is warm and moist. As they meet, because of their differences in their properties, they cannot mix. They tend to create what we call a moisture front, which is a boundary separating the two different air masses. This one, because of its warmth, is less dense. And this one is denser. Because of the differences in temperature, this one is less dense because it's warm. This one is cold, it's more denser. It means this one is going to undercut. And this one is going to be uplifted. As this one is uplifted, because of its moisture content, it's going to reach condensation level and it's going to create clouds that are rain-bearing. So we have on the eastern side of the moisture front, we have rainfall bearing clouds on this side. And this side will have stability. It will be stable. And the moisture front will move in that direction to the east. As more and more cold air is fed into the system, it's going to drive the weather system further to the east, and is going to cause the conditions to move as more moisture is fed into the system is going to move further to the east. Right. So given this situation, we are basically describing what happens with the meeting of the warm and moist air from the South Indian high pressure and the meeting of the cold and dry air from the South Atlantic high pressure, giving us the moisture front and also giving us what we call the line thunderstorms. Is also an important concept. We also have what we call the line thunderstorms, right? These line thunderstorms, they happen on the east. We are having a series of thunderstorms occurring on the eastern side of the moisture front, right? That is basically the description of the weather system. We call it traveling disturbances. The weather system is regarded as traveling disturbances associated with summer conditions. Is traveling disturbance which happen during the summer season. This is typical of summer conditions over the interior. It happens during the summer season where we have this traveling disturbances. Right. That is the situation. Now let's go to the questions and try to figure out from what we have been explaining. We want to highlight and figure out the correct responses from the given options. Right. Number 1.11, it says the sketch above indicates the development of what develops in that system. Is it line thunderstorms, isolated thunderstorms, or radiated fog or frost pockets? The correct response is line thunderstorms, according to what we have been discussing. We have a series of thunderstorms occurring on the eastern side of the moisture front, which is a line thunderstorm situation. So it's correct for line thunderstorms. Right, move on to the next question. Line C represents dash, and the air circulation is dash. Right, if we check on line C, we are seeing that our C is indicating the movement of air from the South Atlantic high pressure going into the interior. So what kind of winds are they? They are coming from the ocean going into the interior. And we are also seeing that there is a circulation pattern which is happening because of the subtropical anticyclonic system in the southern hemisphere. So the correct response for line C represents its onshore winds. Onshore winds coming from the ocean getting into the interior, and the circulation is anti-clockwise, like what we have indicated. The circulation of air out of the high pressure cell in the southern hemisphere is anti-clockwise. It reverses the movement of the clock. So the correct response must match item number 1 and item number 4, which gives us the correct response as letter which gives us the correct response. It's onshore and anti-cyclonic winds. Right. That should give us the matching response for the correct response for the item, which is item number B. Unfortunately, there is an errata which I did not present here. The responses here were supposed to be matched on the errata, and the errata, unfortunately, is not here. But the correct response must match item onshore and item anti-clockwise. Unfortunately, our responses, they don't have a correct response. But what you should master here is that it's onshore because the winds are coming from the ocean getting into the interior, and also the circulation out of the high pressure cell is anti-cyclonic. There is an errata for that particular question. Right, let's move on to question number 1.1.3. The winds at B are dash and results in high level of what? The winds at B, right. Let's look at B. Item number B, we have said the winds at B, we have said they are warm and moist because they are coming from a warm ocean. They are warm and moist from the South Indian high pressure cell or South Indian anticyclonic cell. So they are warm and moist. That is our first response. So it's warm and moist for our first response. And they result in high levels of what? Warm and moist winds, they result in high levels of condensation. When they reach the dew point level, they cause condensation, which is now the transformation or the change of the moisture in the wind into clouds. So we are saying the correct response must match item number 1 and item number 4, which gives us the correct response as letter C. Right. Number 114, line A is A. Right, let's go to our illustration and check for line A. Right, if we check our line A, we can see A is here, is demarcating the meeting of warm and moist air and the meeting of cold and dry air from the South Atlantic high pressure. What kind of a demarcation or a front is that? We call it a moisture front. It's called a moisture front. So line A is a moisture front according to the illustration. It's a moisture front. Right. We move on to the next question. The weather conditions at A. Weather conditions at A. We look at A. On this side is the western side of the moisture front. This is the eastern side of the moisture front. Right. On the eastern side, there is condensation, there is movement of air, there is upliftment of air into the upper atmosphere, causing condensation and creating rain-bearing clouds. That is instability. And on A, we have cold and denser air, which creates stable conditions. So if we look at A is on the west, A, the weather basically is stable. We have stable conditions on A. The weather is stable. We have cold and dry air, which is denser, which has no tendency of upliftment. So the weather conditions will be stable in the western side and will be unstable on the eastern side where there's upliftment, formation of clouds and formation of rain-bearing clouds, and also the realization of rainfall. Right, we move on to number 1.16. 1.16 says the air mass at sea. Air mass at sea is dash and is influenced by. Right, let's go to our diagram. Air mass at sea, we are seeing that air mass at sea is coming from the South Atlantic high pressure. We know that from the South Atlantic is influenced by the cold Benguela currents. We have cold and dry air from the South Atlantic high pressure. So our response, the air mass at sea is cold and dry, which is item number 2, is cold and dry. We check, we are on item number 16. It's cold and dry because of the conditions of the Benguela currents and is influenced by the Benguela currents. The air movement, the movement which happens over the South Atlantic high pressure cell is influenced by the movement of the water, which is also partly influenced by the influence of the air. It happens from the southern pole, is this direction, from the South Pole. And this one is from the equator. So we tend to find that this high pressure cell is influenced by the movement of air from the southern polar region, which is a cold region. So the water which is in the Atlantic Ocean is basically cold because it moves from the southern pole. From the polar region, it drifts northwards. And from this Indian Ocean, the water is drifting gradually from the equator, which is a warm region. So we have warm air here and warm water over the Indian Ocean, and also have cold water because of the influence of the cold Benguela currents on this side and the influence of the Mozambique current on this side here. That is what influences the temperature of the two different oceans across the board. Right. We move on to number 117. Dash clouds will form on the east side of line A. Line A is here. We are looking at the eastern side here. What kind of clouds are going to form? We have rain-bearing clouds because of the upliftment of warm and moist air on the eastern side of the moisture front. And as a result, our rain-bearing clouds, we know that we have the cumulonimbus clouds. The cumulonimbus, they are heaped clouds which are rain-bearing. Because of the upliftment of the warm and moist air, the clouds will be of large vertical extent. They will be extended vertically because of extensive upliftment of the warm and moist air. And as a result, those clouds also are rain-bearing because of the moisture which is contained in the air which comes from the South Indian high pressure or the South Indian anticyclonic cell. Right, we go on to question number 1.2. We are going to do an analysis of the illustration before we answer the question. We're going to do a short analysis of the question. Right. As we are seeing here, this is a valley climatical situation. Right. Valley climates, we are looking at the climatic conditions that do happen in low-lying areas, in valley areas. Right. We see that there is A, and A is moving to the, this is what we call the valley side at A. All right. We are saying at A, this is the valley side. And this is also the valley side. And this is the valley floor. So we are saying there's a movement which is happening on air, which is from the valley side to the valley floor. The air moves down from the valley side, getting into the valley floor. Typically, what happens here is the air which moves from A going to B is called a katabatic wind. Right? What happens is katabatic conditions, they happen, typically valley conditions, they are typical of winter conditions. And what happens is during winter, there is extensive cooling of the valley sides because of terrestrial or long wave radiation. And because of that, the valley sides, they get excessively cooler or cold. And the air which is immediately above the valley sides, they are cooled and they become more denser. And because of gravity, the air tends to move down to the valley floor because of its density. It's now very cold and it gains more weight, it becomes more denser, and because of gravity, it has to drift downwards. It moves into the valley floor. As it goes into the valley floor, there is already air which is there in the valley floor, which is warmer. What is going to happen now because of differences in density? This air coming from the valley side is more denser. It has got more density, which means it's going to displace the warmer air, which is in the valley floor. And in the valley, it means the warmer air is going to uplift, going to subside because of the coming of colder air into the valley. This one, because of its warmer conditions, is going to be uplifted because it's less denser. It uplifts and it creates what we call an inversion layer. It creates now an inversion layer, which is an inversion layer. We are looking at a belt of warm air which is trapped between two air masses of cold air. At the bottom, there's sinking cold air, which is coming from the valley side. And we are looking at winter conditions here. We also have sinking air from the Kalahari high pressure cell. There's sinking air coming from the Kalahari high pressure cell, and also there's cold air from the bottom of the valley, which has been created by gravity from the sides of the valley. So this is a belt of warm air, which is trapped in between two air masses which are cold. This one is cold, sinking air from the Kalahari, and the cold air which has sunk into the valley because of gravity from the valley sides. So that's the situation of an inversion layer. So that basically describes the situation of the valley climatic conditions. So we need to go and look at the questions and look at how those questions were supposed to be answered based on our description of the illustration. Right. We go to question number 121. Winds that blow from A to B, like what we have said here. From A to B, we have said those winds are night winds, which are katabatic. And what you should note also, there's an illustration of a moon here. This is illustration of a night situation. This moon, it indicates that it's night. We know that it's katabatic at night, and it's anabatic during the day. So this illustration of the half moon was supposed to also guide you in determining the kind of wind which happens. It's katabatic at night and anabatic during the day. Right. These winds develop during cold winter nights. They happen during cold, calm nights. When the conditions are calm, cloudless, clear winter nights, that is when we have those conditions. Right. Area C represents this area C here. We have talked about that. This is an inversion layer. All right. Frost pockets will form at point A or B. Right. Let's go to our diagram. A is here on the valley side. B is on the valley floor. What you call frost pockets, we are looking at a situation when the temperature falls below freezing point. The moisture which is contained in the air is going to convert into frost, is going to freeze because the temperatures are below freezing point. And ultimately, if there is any moisture in the air which is around that area, the moisture is going to convert into frost, frost, which means frost pockets. We are looking at a situation that happens in the valley floor. So it's B. For that response is going to happen at B. We have frost pockets forming on the valley floor. Right. Mountains cool through the process of which process results in the cooling of mountains. Right. Mountains, they cool due to terrestrial radiation. Terrestrial radiation is the same as long wave radiation. When we have the loss of heat from the surfaces during the night, that is a form of terrestrial or long wave radiation. That is the one responsible for the cooling of mountains. They receive the heat during the day when we have sunshine, but at night, because we no longer have sunshine, there's no more incoming heat. The heat which has been absorbed during the day is going to be lost through long wave or terrestrial radiation. That is how the mountains cool. Right. We move on to the next question. Dash causes A to move from point A to B. From point A to B, what causes A to move from point A to point B? I think we have discussed about that earlier on. This is caused by gravity. The air becomes denser because of the cool conditions, and as the air becomes cold, it becomes heavier and it tends to sink due to gravitational force. So it's because of gravity. That is why the air will have to move from point A to point B. It's because of gravity. Right. When condensation takes place at B, dash will form. When condensation takes place at B, here, when there is condensation taking place. Condensation, we are saying, is the transformation of moisture or the change of condition of water, which is moisture, in the air into water droplets. What forms if the air changes from from being moist air into water droplets? It forms what we call radiation fog. Radiation fog, it forms because of terrestrial radiation, the loss of heat on the ground surface because of the night conditions. It results in the air immediately above the surface getting to cool down because of the cooler ground surface. And ultimately, there will be formation of radiation fog. Right. That is question number 127. We move on to number 128. Dash forms on the valley floor when temperature drops below 0 degrees Celsius. When temperature is at 0 degrees Celsius, we know that 0 degrees Celsius is the freezing point. When we have moisture in the air and the temperature is at 0, we know that the moisture get to freeze to form ice. So when it drops below, it forms frost. That is how our frost pockets form in the valley floor. Right. So that is basically how we're supposed to answer question number 1.2. Right, we move on to question number 1.3. Right, we will also analyze the infographic. It's based on an infographic, question number 1.3, which we should analyze and which we should try to figure out before we go into responding to the questions. Right, it's based on a tropical cyclone, Cyclone Dikeledi, formed in the Southwest Indian Ocean on Thursday, January 9, 2025, and is expected to rapidly intensify before making a landfall in northern Madagascar. That's the situation. That's the heading of our infographic. And we have a satellite image, which is illustrated here. This is a satellite image. What we are seeing here is an illustration of the tropical cyclone in the form of a satellite image. And also we have this illustration here of a synoptic map showing the same scenario of the weather system. So basically, these two are relating to what is described in the text there. According to information from DCCMS, the storm is expected to land over northern Madagascar on Sunday, January 12, 2025, before moving into the Mozambique Channel. The notice further indicates that Malawi will experience reduced rainfall over southern parts of central regions in the coming days due to an unstable easterly hemisphere. Right, that is our infographic. We should be able to interpret the text and interpret the satellite image and also interpret the synoptic map of the same weather system is our tropical cyclone. Right, let's go to the questions. The questions, the first question is saying, identify France A and B on the map. Right, we are looking at our synoptic map here. That is our focus area. We want to identify the two fronts. We understand a front is a boundary separating two air masses of different properties. They can be different in terms of temperature. They can be different in terms of moisture content. They can be different in terms of stability. So we have a front at A, which is indicated. What you should note here is this, and you should also note this. That gives us a distinction of the fronts. At A, our A is here. At B, our B is here. At A, you can see that the indication here is a triangular indication of the front. And that one is used for a cold front. So our A is a cold front. And B, a semicircular indication, it indicates a warm front. So it's a cold front on A and a warm front at B. Those are the responses of the two different kinds of fronts. It's a cold front at A and a warm front at B. Right, we move on to the next question. Identify area X on the satellite image. Right, our satellite image, we have said it's here. On our satellite image, we want to identify this area here. This area X, the area indicated X on our satellite image. This area X is the same as this area on the synoptic map. The center of the weather system, the focal point of the weather system. This is what we call the eye of the system. It's the eye of the weather system. The focal point where the weather system circulates. Actually, we understand that a tropical cyclone circulates in a clockwise direction in the southern hemisphere. But we have a center of the system where the circulation is focused on, the focal point of circulation. That is the eye of the weather system. Right, we go on to the next question. Mention the conditions that favored the formation of tropical cyclone Dikeledi in the southwestern Indian Ocean. Basically, this question requires us to look at the conditions favorable for the formation of tropical cyclones. Tropical cyclones, we know they need warm oceans, temperature of around 26.5 degrees Celsius. They need warm ocean current or the warm ocean for them to form. They form at temperatures of around 26.5 degrees Celsius or above. So the South Indian Ocean, we know an Indian Ocean is the warm ocean current and the temperatures are slightly higher, resulting in favorable conditions of the formation of such a weather system. And also we can talk of Coriolis effect, which facilitates the formation of the vortex. Coriolis, we know that tropical cyclones, they don't effectively form within a region of 0 to 5 degrees of the equator because there is minimum Coriolis effect. But after 5 degrees, the Coriolis force intensity or the frequency of the Coriolis force increases. So, because of the increase in Coriolis effect, we tend to find that the circulation creates the vortex, which facilitates the formation of tropical cyclones. And also we can talk of availability of moisture. Because of the warm ocean, there is also availability of moisture, which facilitates the formation of the weather system of a tropical cyclone. So basically, the question requires you to identify factors in the Indian Ocean which are favorable for the formation of tropical cyclones. Right, we move on to the next question. Why do mid-latitude cyclones mostly affect the weather of South Africa during winter? Right, I'll briefly explain. The question basically needs you to relate the position of the subtropical anticyclones to the formation of mid-latitude cyclones, to the occurrence of mid-latitude cyclones over the interior. We know well that over the Southern African subcontinent, we have the two anticyclones affecting the weather system. We have the South Atlantic high pressure on the west and the South Indian high pressure on the east. So because of these two, we tend to find that they happen as blocking systems. They block weather systems from affecting the interior. If they are here and the interior of Southern Africa is here, let's assume this is our Southern African subcontinent with the South Indian here, right? It means if they are here, if the South Atlantic is here, it's blocking all weather systems coming from the west. And also this one is blocking weather systems coming from the east because it's an anticyclone, it's a high pressure system. It blocks any weather system which wants to get into the interior. So in winter, we know that the movement of these subtropical anticyclones, they move with the latitudinal position of the ITCZ. They move with the latitudinal position of the intertropical convergence zone. In winter, our intertropical convergence zone, and in summer, the ITCZ position, it differs. So what will happen is, because of that shift, we are saying a southward shift of subtropical high pressure, allowing westerly winds to dominate. The westerly winds are going to dominate here because of a southerly shift of this weather system. So it depends on the position of the high pressure cell. It affects how the westerly winds are going to affect. These mid-latitude cyclones, they are driven by these westerly winds. So the westerly winds are the ones which determine whether the mid-latitude cyclones are going to reach the interior or not. So the position of the subtropical high pressure is it allows the winds to dominate. So we are saying they allows it allows the westerly winds to dominate. If the westerly winds are dominating, it means they can also drive the mid-latitude cyclones into the interior. But if they are blocked, they cannot be allowing the mid-latitude cyclones to get into the interior. So because of the shift of the high pressure cell, it allows the domination by the westerly winds. And the westerly winds are the ones responsible for driving the mid-latitude cyclones into the interior. Right. Number 136, it says, according to the information from DCCMS, the storm is expected to land over northern Madagascar on Sunday. And what is going to happen? January 12, 2025, suggests the action plan that the government of Madagascar can apply to reduce the impacts of tropical cyclone Dikeledi. What can the government do to reduce or to lessen the impacts that are likely to be caused by tropical cyclone Dikeledi? Right. we are looking at government measures that can be implemented to reduce the impact of a tropical cyclone Dikeledi on the people. There are so many measures there. It's just a matter of selection of what you feel. This is a 2-mark question. You give one response which is explained. So we can say the government can put in place evacuation plans. We can talk of evacuation. Low-lying areas, people must be evacuated. They must be removed from low-lying areas which are prone to the dangers of flooding because of the storm. They must be put to safer areas. They must be put to areas which are safer, which are high-lying. Or you can talk of preparing stocks of food, or it can be stocks of medication, or whatever. The government must put in place stock measures to ensure that people have got enough supplies during the storm situation. Or you can talk of emergency services. The government must ensure that there is sufficient emergency service. Like, for example, the ambulances to take people in case of injuries because of the storm. They must have enough capacity to cater for such emergencies. So we must put in place emergency measures. Or we can also talk of alerting people. People must be alerted. They must be kept alert through media. The different forms of media, either through the radio, through television, through different media like WhatsApp, to alert people to be prepared for the coming storm. They must know when the storm is making a landfall so that they get to take precautionary measures against the side effects which are likely to be posed by the coming storm. So those are some of there are so many that you can talk about, but it's just a highlight of what you can discuss. Then draw a well-labeled cross-section to illustrate the mid-latitude stage represented at C. Right, we go to our synoptic map. C is here. Is at the eye of the storm. And what is happening at the eye of the storm? We are seeing that there is an occlusion. We have an occlusion situation. What is an occlusion? An occlusion is indicated by the existence of a cold and warm front indication on the same line. This is cold and this is warm. But we are seeing that they are now coexisting on the same line. Previously, the warm was here and the cold was there. But now they are coexisting. They are now on the same line. This is what we call an occlusion. It's an occluded stage of the formation of the tropical cyclone. So what we want to do there is to illustrate the formation, the formation of the storm in terms of the level of the stage of formation of the storm. Right. So when we're talking of the formation of the storm in terms of the occluded stage, we are saying we draw something like this. We draw something like that. This is our ground. And on this is our cold front. And this is our warm front. And out of these two, we have called and we have cooler, cool air. And this is our warm sector. That is basically what you should illustrate. You should illustrate the air which is on the western side and the air on the east, and also you must illustrate the warm sector and also indicate the direction of movement of the weather system like that. That is basically what is required by the cross-section. The cross-section requires you to illustrate an occluded stage of the weather system. Right, let's go to the number 1.4, which is the next question. The next question is based on refer to Fig 1.4, showing the position of the inversion layer in winter and in summer. Right, we have the differences in the level of our inversion layer during winter conditions and during summer conditions, right? Because of the changes in the intensity of the Kalahari high pressure cell, right? So I will explain briefly on this illustration, right? This illustration, the first illustration, is indicating what we call the winter conditions. The inversion layer is lower, is below the escarpment. Inversion layer gets lowered below the escarpment because of strong subsidence. There is strong subsiding air because of the intensity of the Kalahari high pressure cell, such that the inversion layer gets lowered below the escarpment and it blocks incoming air from the South Indian high pressure. And during summer, because there is weak subsidence, the Kalahari high pressure cell is not active enough. The inversion layer will get elevated. It's uplifted such that it allows for the incoming of warm and moist air from the Indian Ocean. That is basically the difference between the position of the inversion layer during winter and during summer conditions. So this is summer, this is winter. In summer, there is weaker subsidence, the inversion layer is elevated, the Kalahari high pressure cell is vertically displaced. And in winter, the Kalahari high pressure cell is active and is forcing the inversion layer lower below the level of the escarpment and is blocking the coming in of warm and moist air from the Indian Ocean, giving us clear conditions over the interior. And it gives us unstable conditions over the interior in summer because the incoming air is going to cause condensation and creates unstable weather conditions over the interior. That's the distinction between the two. Right, let's go to our questions. Right, define the concept temperature inversion. When you are defining a temperature inversion, you define it as an increase of temperature with height. As height increases, temperature also increases. That is an temperature inversion. Or it's a reversal of normal temperature profile. Normal temperature profile in the troposphere. We know that in the troposphere, the temperature profile must be negative. As we increase in height, our temperature must decrease. That is the normal temperature profile. But if it's going positive, we are increasing height, the temperature is increasing. That is now a temperature inversion. So it's an increase of temperature with height, with an increase in height. That is an inversion. Or the reversal of the normal temperature profile in the troposphere. We know that in the troposphere, the higher we go, the cooler must it become. But if it becomes water as we go up, then it's a temperature inversion. Right. Does the sketch X or Y represent stable conditions? Where do we get stable conditions? Is in the first sketch. It's sketch X. Stable conditions, we get them in X. Here, because there is no incoming A, the A is blocked. We have stable conditions. Here is unstable. Right? Account for the strong subsidence in sketch X. Strong subsidence. Why do we have strong subsidence here? This is winter conditions. The air is cool, or rather is cold. Cold air is denser and it tends to sink. There is cold air which tends to sink because of winter conditions. The Kalahari high pressure cell is more active because of cooler conditions. That is what creates the strong subsidence in X. Then weak subsidence in Y, it's summer conditions, the temperatures are high, there is higher temperatures. So the air is less dense and it cannot effectively sink down because of its density. The difference there is caused by temperature. If it's cold, it's winter conditions, the air is cool and it's more denser. It tends to sink. But if it's summer, the air is warmer, is less dense. It does not have a tendency of subsiding. It's weak subsidence because of higher temperatures. Right, we go to the next question. Explain why backwinds are most likely to develop in sketch X. In X here, why do you have the backwinds forming? The backwinds will form because of the strong subsidence. The sinking air is going to hit adiabatically as it goes down the escarpment. There is strong subsidence and that subsiding air is going to hit adiabatically. That is why the backwinds are likely to develop. The backwinds, they develop during winter over the coastal areas because of sinking air. This sinking air here, we are saying, as it sinks down, again it's going down the escarpment. It's strongly subsiding and it's heating up adiabatically because of changes in pressure as it goes down. It tends to heat adiabatically and it's going to cause the backwinds as it goes to the coastal areas. Discuss the negative impacts of backwinds on the physical environment. The question is asking about the physical environment. There, on the physical environment, you can talk of fire dangers. The backwinds can cause fire, which will damage the environment, which will destroy the environment. It increases the chances of fires, of wildfires. And those wildfires are going to damage the environment. Or you can talk of vegetation damage. Because of stress, moisture stress. The vegetation can be damaged because of moisture stress. There is excessive heat and there is excessive transpiration and the moisture content in vegetation is going to get reduced and the vegetation can be damaged because of that. Or you can talk of the disruption of the ecosystem. The balance in nature is going to be disturbed because of the excessive heat created by the backwinds. Or you can talk of evaporation rates, increased evaporation rates. How do they affect the physical environment? They cause reduced soil moisture content. The soil moisture content is going to get reduced because of high evaporation rates. Because of high temperatures, there's high evaporation. The moisture content of the soil is going to be affected ultimately. And that is a negative implication. Right, let's go to the next question. It's talking about urban heat islands. Right, it says define the concept urban heat island. Right. The text is saying the temperature difference is usually larger at night than during the day and is most obvious when winds are weak. One of the main causes of the urban heat islands is the fact that there's little bare earth and vegetation in urban areas. That is the situation, and you can see the temperature profile. The temperatures are higher here. You see this is a built-up area, which is an urban area. The temperatures are higher. They are around 23 degrees Celsius on average. In the rural, they are lower, below 20. And as you go again to the rural, they go down. And then in the suburban area, you can see they are slightly higher again. Right. So define the concept urban heat island. When you're defining an urban heat island, we are saying it's an urban area whose temperature is higher compared to the surrounding rural area. The concept here is about temperature. What you must note when you are defining an urban heat island, talk about temperature. It's an urban area whose temperature is higher compared to the surrounding rural area. You are comparing an urban area to a rural area. In urban heat, the temperatures are higher in an urban area compared to the surrounding rural areas. Quote the main cause of urban heat islands from the extract. Right. What is the cause here? Is the fact that there is little bare earth and vegetation. That is the cause. One main cause of the urban heat island is the fact that there is little bare earth and vegetation in urban areas. Done. Give reasons why central business districts account for the highest temperatures than other parts of the city. The CBD, why does it have higher temperatures compared to other parts of the city? Talk of the vehicles. The vehicles are many in the urban CBD. Those vehicles, they emit pollutants which are responsible for absorbing heat. And talk of the built-up areas. Urban area, the CBD is more built up. The buildings, they tend to absorb more heat and they cause an urban heat island condition compared to the surrounding area. Talk of less vegetation in the CBD, which has a cooling effect. Or you can talk of population in the CBD. There's so many factors that you can attribute in the CBD, which makes it have a higher temperature compared to talk of tall buildings in the CBD. Explain the negative impact of urban heat island on city dwellers. How are city dwellers affected by the higher temperatures? You look at how people are affected by the higher temperatures as they stay in the urban areas. You look at aspects like dehydration. People are dehydrated because of the high temperatures. The high temperatures cause them to be more dehydrated. Talk of health complications. People who have got health complications are worsened. They have got a worse situation to face because of the excessive temperatures, which are prevalent in the CBD. Right, we go to the last question. Suggest strategies that the municipalities and city dwellers may implement to reduce the effects of urban heat island. What can be done to reduce the effects of the urban heat island in the cities? You can talk of the creation of the parks, where we introduce vegetation and water bodies so that the temperatures are lower. Talk of construction material, we can look at alternatives like thatched roofs, which have got an effect of reducing the temperatures in the urban area. Talk of rooftop gardens, it can also assist in reducing the effect of urban heat islands. Right. So when you're looking at reducing the effect of urban heat islands, we are looking at measures that can be put in place to try and reduce the temperatures. You can talk of decentralization, of activities like industries or commercial decentralization. It can also assist. When we decentralize, you are saying we should move industries out of the CBD, or we move commercial activities outside the CBD so that we have less congestion in the CBD and also ultimately reducing the impacts of urban heat island. Right. So basically, that is the outline of what we're supposed to look at in the paper. We did not exhaust all the responses. The possible responses, as long as they are geographically reasonable, they are within the spectrum of the correct responses. So in our discussion, we have tried just to highlight how you were supposed to respond to the given questions and ultimately how you were supposed to answer the questions. We know well that our paper is a 60-mark paper and it's very